Okay, we'll finish this 5-2 today. We're going to talk about these special cases. Oh. What time do we get out of here? Right now? 41. 41. Yes. Look in your little.
It's 41.
Okay. All right. So I see I have 3 equations, 3 variables. So none that just jump out as really easy. I'm going to pick the top 2, and I'm going to multiply it by -3, so I can get rid of this disease. So I'll write that here. Okay. So 2x minus y plus 3z equals 8, and then I'm going to multiply by -3. So -9x plus 12y minus 3z equals -12. Okay, add down. So your z's eliminate. All right, that's -7x plus 11y equals -4. So now I need to choose 2 more. I'm going to use the middle one again because I only have to multiply 1 equation. And this time I'll multiply the middle one by, what should I multiply the middle one by so I can eliminate z? 6. Yeah, 6, good. So since I eliminated z in the first set, I need to eliminate z again. So that's 18x minus 24y plus 6z equals 24. And then -4x plus 2y minus 6z equals 5. Now I can add down. That's 14x minus 22y equals 29. Okay, so now this comes back here, and I have a normal 2x2 system. So to eliminate, what should I multiply the top equation by? 2. Good. So that's -14x minus or plus 22y equals -8. Add down. And I see that my variables cancel. Giving me 0 and then 21 here, which is false. So because I got a false statement, this one will have no solution. Or you can say inconsistent. So anywhere that happens, that you get a variables cancel and you get a false statement, you can stop and say no solution. Because sometimes it could have happened here. It could have happened here. All 3 may be eliminated and you got a false statement. Then you could stop there and say no solution. Okay, so at any point in your problem, when you solve, and it's false, you can say no solution. Okay? Questions about that one? Okay. We have to talk about then the infinitely many solutions. There's two types of dependent solutions. So two types that could give us infinitely many solutions. One of them is linear dependent and the other one's coinciding dependent. Okay. So the one we're going to look at is first is linear dependent. And I'm just going to preface this by saying that this type of problem is probably the hardest type from the first two sections, 5.1 and 5.2. Okay? So if this seems a little bit hard, that's because it kind of is. Okay? So you might want to practice it. Okay. So linear dependent systems have two equations that are different, but then the third equation is coplanar, meaning it's a duplicate of another equation. And by duplicate, we mean it's not necessarily the exact same, but it's just multiplied by a scalar or something, so then everything would cancel. Okay. But if you just start with two equations with three variables, that is a giveaway that it's linear dependent. Okay, so like this one, two equations with three variables will be linear dependent. So this is like taking off the third equation that would be a duplicate of one of those two. Okay, so we're not going to be able to get just values for x, y, and z. There's not a third equation to help us do that. So what we're going to be getting is just answers for the variables, but in terms of one of the other variables there. Okay? And it'll be like little linear equations, and that's why what makes it linear dependent. Alright, so when I see this, the only thing I can do is try to just eliminate one variable. And what looks like the easy one to eliminate? Yeah, so let's start with that. So eliminate one variable. Okay, so in this case, we're going to eliminate y. So I'm going to try to give you general instructions here in black, and then as we go through this specific example, over here, eliminate y. Alright, so then that gives me 7x plus 7z equals 14. That y can be eliminated? Yeah, I mean, technically, x could be eliminated too. You just have to multiply first. So always eliminate one variable first. Okay. So I don't have any other equation that I could pair to get, another equation with just x and z, like we did on the last example. So right here, I'm kind of stuck. So I have to go ahead and start solving for one of the variables. So my next step is taking this, and I'm going to choose a variable to solve for. So I'm going to choose either x or z. Okay, so I have 7x plus 7z equals 14. So let's choose x. It doesn't matter, you could pick z. It will make your answer different depending on which one you choose, but it does not mean it's incorrect, okay? As long as you do all your work correct, it doesn't matter which one you choose. All right, so if I'm going to solve for x, then I need to subtract 7z. So negative 7z plus 14, and then divide by 7. So that's negative 1z plus 2. Okay, so right now I have an x equals. So I still need to solve for every variable, so I need to have an x equals, a y equals, and a z equals. But they're going to look like this, like little linear equations. Okay. So now I have x, and I have x in terms of z. So here is, I'm going to say, identify the parameter, and I will talk about that once we get to the end. So right now, what I'm identifying is what is x in terms of, and it is in terms of z. Okay, so I'm going to say, z equals z. Okay, so x is in terms of z, so every other variable has to be written in terms of z. Well, the only way to write z in terms of z is just this, z equals z. Okay, so terms of z. Okay. I will explain this more once we are done and we get to the end. All right, so I have an x equals and a z equals. I need a y equals. So substitute values into one of the originals. It doesn't matter which one. To find the third variable. And we are going to leave in terms of our p. Which in this case is z. All right, so I'm plugging in this x equals and z equals, so I'm plugging these in right here, z and negative z plus 2 for x and z into one of the originals. Okay, so that's 4x. So 4 times negative z plus 2 minus y. So I'm choosing the top equation here. Choosing this one. Plus 2z equals 9. Okay. I have an x equals and a z equals. I need a y equals. So I'm going to get y equals. I'm going to distribute, combine like terms, and get y equals. And it will be in terms of z, which is what I wanted. So negative 4z plus 8 minus y plus 2z equals 9. Combine your like terms. remember you want y equals, so I have to add 2z to both sides, so I'm going to kind of write out this step. I think I wrote it. So now I have 8 minus y equals 2z plus 9. Subtract 8. Negative y equals 2z plus 1. Divide by negative 1, so that means switch your signs. Negative 2z minus 1. And there is my y equals. Okay, so I have all my answers now. Now it's just a matter of writing my solution in terms of a parameter. Now let me go back and summarize this though. So what I did is I plugged in x and z into the original, the top one. It doesn't matter, you could have picked the bottom one. And solved for y. I needed y. I had x and z and I needed y. Okay, then our final step, what are we on? Type. Write solution in terms of a parameter. Okay. X, Y, Z. So I'm saying my ordered triple, my X, Y, Z, are X is negative Z plus 2. Y is negative 2Z minus 1. And Z is Z. So I have to say though, in terms of a parameter, it means you use the variable P. Okay, but this case, P is Z. My single variable, what I wrote my equations in terms of, that's my parameter. So I can do this. So X was negative Z plus 2, so negative P plus 2. Y was negative 2Z minus 1, so negative 2P minus 1. And then Z is our P. So here's my solution. It is dependent. It has infinitely many solutions because you can choose anything for P. Okay? You can plug in anything you want for P. And then, but it is linear dependent because X and Y are dependent, are these linear equations based on what P is. So, for example, one second. If I say, I have to start with what P is. So let's say I want Z to be 3. Okay? Then Y would be negative 2 times 3, so negative 6 minus 1, negative 7. And then X would be negative P, so negative 3 plus 2, negative 1. So this is one example of a solution to the system. If you plug these in to the originals, you will get true statements. Okay? What was your question?
I'm good.
Yes.
On my test and stuff, if you want us to put equals and more variables.
So on the test, no, I don't have to see this, but you might want to just to help you. So your P will be whatever your single variable is here. Yes.
So can you pick whatever variable you want?
Yeah. So your parameters then will look a little bit different, but the ordered pairs or your ordered triples would end up being the same. So let's say back up here. I mean, we wanted to eliminate Y because that was easy here. You could have done X if you wanted, or Z, but it was just easier to do Y. But let's say we chose Z here instead, and we solved for Z. Then Z would be written in terms of X. So X would be our P in that case. Yes?
How do you do ordered triple?
This part here.
No, the numbers below.
Oh, yeah. So I just picked a P. I picked a number for Z. And this is why there's infinitely many solutions, because I can choose anything I want for this. This is just one example of an ordered triple that would work in that system of equations. But because I picked 3 for P, this had to be -7 and this had to be -1 based upon on these equations. Yeah, I really just said, let's say P is 3. But I could say P is 0. And then I just, plugged them in. Okay, so if let's say if it's 0, then I would have -1 and 2. That's another ordered triple that would work in my equations. Okay. Okay, we're going to look at the other type of dependence, and that might help a little bit with the linear dependent. Okay, so linear dependent systems have 2 equations that are identical. Or we could say it the other way, where 2 equations are different. So if you're starting with just 2 different equations, then it's linear dependent. Okay, coincident dependence, all 3 are identical. And by identical, we don't necessarily mean that they are the exact numbers, but they're just multiples of each other. So let's just look at this and solve how we normally would, because there's 3 equations, 3 variables. I'm going to take these 2. And I'm looking at y right now. So I want to eliminate y, I'm going to multiply the bottom one by 2. So I'm going to take 4x minus 2y plus 6z equals 14. Here I have negative 4x plus 2y minus 6z equals negative 14. These are identical because I get 0 equals 0. If you look, this bottom one is really just double this middle one. I mean, and by negative, so it's multiplied by -2. So it's multiplied by the same number all the way through, which means it's identical. Okay, that tells me that this system will be dependent. I don't know if it's coincident or linear yet until I check 2 other ones. And I have to check 2 other ones. Right now, this just tells me that 2 of them are the same. So I'm going to check 2 other ones. And I still want to use this bottom one because I think it's easiest. So I'm going to do the top and bottom. And I'm going to multiply the bottom one this time by 3. Okay. Now, again, I get 0 equals 0. So that tells me that all 3 of them are the same. So now I can say coincident dependent. And we'll write these in set notation, but this is not as hard as the parameter. So you use your braces, x, so you say any ordered triple, x, y, z, such that, and then you just pick any of the 3 equations, any of the 3 original, I'm just going to pick the top one, but you could choose any three. So x, y, and z, any order triple is good as long as it's 6x minus 3y plus 9z, thank you, equals 21. And this So I'll scroll back down in just a second. You could have a linear dependent system that has three equations with three variables. It would be linear dependent if you get 0 equals 0 for two of the equations, but then when you go down here, that doesn't happen. You're just able to eliminate one variable. So starting here would be like starting here. Okay? Now, if you just start with two equations, you know it's linear dependent. It's just taking off that extra step of having the identical equation there. Okay? Any questions so far about that? Okay. Let's talk about a word problem. The biggest thing is let's get it set up. If we have time, we'll solve, but the setting up part is usually the hardest part. Okay, so you start off with these by figuring out what your variables need to be. So in what year did each end? So let's say W is when World War II ended. K is when the Korean War ended. And V is when the Vietnam War ended. Okay. Alright, now let's set up our equation. So three variables, you want three equations. Okay, if you sum the years that each conflict ended, the result is 5,871. How would I set that equation up? If you sum the years that each one ended, W plus K plus V, 5,871. Good. Okay. The next one. The Vietnam War ended 20 years after the Korean War. Okay? So, which one has more years? Vietnam, right? So, I want to make an equal statement. So, it ended, if I wanted V to be equal to K, Vietnam has 20 more years, so I'm going to subtract. Okay? You could either add 20 to K or subtract it from V. So Vietnam War, to have an equal statement, it has 20 more years. So for V to be equal to K, you have to subtract the 20. So let's say, this was 1975, this was 1955. So for those to be equal, you'd have to subtract the 20 here. Okay? And so then I can do the same thing for this. But this time I'll do V minus 28. equals W. The reason why I write it like that instead of the other way is because now I can substitute, if I wanted to solve this, now I can plug this in for K, and this in for W. So that's B minus 28 plus B minus 20 plus B equals 5,871. And I can already get B. I'm down to just one variable there in that equation, so I can solve for B. Okay, we'll stop there.